So this video is going to be on differentials. So when the tangent line of the graph of f at the point C, f of C, is used as an approximation of the graph, that x minus c quantity, we call it the change in x, right? It's x minus x1 in point slope form, but in this case we're saying x minus c. And we're going to denote this change in x with the symbol delta x. Delta in math is generally a Greek letter that we use for change. So we're talking about the change in x. So if I say that this value is c, we're going to say this delta x, then this is c plus delta x, right? We see this a lot with f of x plus h minus f of x over h, except we do the x plus delta x over delta x, right? So we know what delta x means. Now when delta x is small, that change in y, which we're going to call delta y, can be approximated like this, right? We know that delta y is f of c plus delta x minus f of c. We also know that this can be approximated with that tangent line as f prime of c times delta x. We talked about that, right? Now, for this approximation, the quantity delta x is traditionally denoted with dx, and we call it the differential. So f prime x dx is the differential of y. So if we change that delta x into dx, we get f prime of c dx. This is kind of the way we're used to seeing it. I'm going to show you something and then I'm going to show you something else. But what we were going to say is, okay, if we let y be a function differentiable on an open interval containing x, the differential of x, which we call dx, is any non-zero real number, and the differential of y is given as dy equals f prime of x dx. Now, I want y'all to think about this. This is not mathematically kind of accurate, but I want you to think about this. Dy dx equals f prime, right? Now, this is, I'm going to reiterate this, and I can't stress this enough, that this has no basis in mathematics, what I'm fixing to do. But it looks like mathematics. What happens if I multiply both sides by dx? Which is not something I can do because dy dx it specifically means something. But if I could, I would wind up with dy equals f prime of x dx, which is true. So, although it has no mathematical basis in reality, it is still something you can think of as, how do I get that dx over? Now, this tells us a couple of things. First thing, delta y is an approximation for dy, but we can also, since I know that dy is f prime x dx, I can say that as well. So let's look at something. We want to let y equal x squared, and we want to find dy when x equals 1 and dx is equal to 0.01. And we want to compare that value with delta y. Okay? So we're going to look for dy and we're going to look for delta y. So first off, let's find dy. So I know that dy equals, in this case, y prime dx. So y prime is 2x, right? I know my x is 1, so y prime equals 2 times 1, or 2. I know that dx is 0.01, so I get that dy equals y prime, which is 2, times dx, which is 0.01. I get dy equals 0.02. Now let's see how that compares with the actual value of delta y. Well, how do I find delta y? Well, I know delta y is f of x plus delta x minus f of x, right? So, in this case, x equals 1. So, f of 1 plus 0.01, because that's 1 plus delta x minus f of 1. So this just means I'm going to plug these values into my y. So this is going to be 1.01 squared minus 1 squared. Now, let me get my calculator up if I can find my... There we go. So we'll say 1.01 squared is 1.0201 minus 1 gives me 0.0201. Pretty close approximation. Notice it's not exact, but it is a pretty good approximation. Now, if you have any questions about how to deal with dy, how to deal with delta y, just shoot me a reminder or ask a question in class.